All right, so we're gonna let that be. Let's hit done. Let me share my. Let me check the chat real quick. Let's see. Okay, so okay, I'll address this during my announcements. Let me share my screen. Start the broadcast. And last video. Okay, we'll start here. That's okay. All right, so greetings, scholars. Hope everyone had a good weekend. Sorry about the late startup. Let me see. So there was a question in the chat about, are we able to purchase Pearson online? My recommendation, if you're trying to access the discount, you have to purchase it through the Morehouse bookstore. So for like $100, you'll get 2 years of full access to my math lab, right? 2 years of full access for $100. But I think you have to get the access code through. You have to purchase the access code through the bookstore. We are at week 6, right? So this week we're going to be working on section 1.5. I think at week 8 we have our exam 2, which counts as our midterm. We'll talk about that more as we get closer to it. Okay, as usual, if you have questions, feel free to either unmute yourself or type in the chat. Otherwise, I'm gonna just kind of go ahead and get started. Let's see if I can like this. No, you're not gonna be there for me. You single page. There it is. Okay. All right. So we're continuing chapter 1. I think we have like 2 more sections. One more after this section. Chapter 1 is over graphs and functions. And so today we're going to be working on section 1.5, transformations of functions. A few objectives. 1, we'd like to define transformations of graphs. 2, use vertical or horizontal shifts to graph functions, use reflections to graph functions, and use stretching or compressing to graph functions. So I think last time we worked on section 1.4, which was a library of basic functions. And so now we're going to take that collection of functions and apply these different transformations to those. And so this is how they do graphing, or how we do graphing in College Algebra. Okay, so let's look at this next concept. So if a new function is formed by performing certain operations on a given function f, then the graph of the new function is called a transformation of the graph of f. So let f of x be the absolute value of x, g of x be the absolute value of x plus 2, and h of x be the absolute value of x minus 3. Sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. Anybody know the shape of the absolute value function? It looks like a letter in the alphabet. What letter does it look like?
A V.
It's like a V, right? So one of the basic functions we talked about was what? X squared, which is like a U-shaped curve. So absolute value, which is like our f of x, that's going to have a V shape. So then we're going to see how, if we add a positive, there's like a total of 10 different transformations, right? So the concepts behind the transformations are simple, but it's just not easy because it's information overload. All right, so it's like 10 different transformations. So I think here we have 2 of them. So we're going to see how when we add a positive on the outside of our basic function, and when we subtract a positive on the outside, how it affects our graph. Okay, it's decent. I should get this to class. Okay. Dusting off the cobwebs from the weekend. Like, these are... Okay, so let's start this out by making a table. Now let's see. So we'll have our x. Let's do a bar. Let's look at our f of x, our g of x, and our h of x. Okay. We're just going to choose several values of x. So I'm going to let x be, like I'm thinking, -3, -2, -1, 0, 1, 2, and 3. Okay. So then, can anybody tell me the absolute value of -3? So absolute value.
3.
3, right? Yeah, absolute value is the positive distance away from 0 a number is. So -3 are 3 units away from 0, right? So the absolute value of -3 is 3. Absolute value of -2 is 2, 1, 0, 1, 2, 3. Again, absolute value is the positive distance a number is away from 0. So now for G, we're going to take those results and add 2 to all of our results, right? So 3 plus 2 is 5, 4, 3, 2. Then I think it repeats from there. 3, 4, 5. Okay. So we're going to plot 3 different graphs, and let's do G in green. Okay. And then H. Anybody got when you see H, what color comes to mind? Hey, Google, give me a random color.
Orange. Orange is a bright color with a red hue and can be the color of fire or a traffic cone. It is also a warm color, just like the warm colors associated with spring and summer.
I thought she was about to try to flatter me. She just goes into this rant. I'm like, yo, Siri, please spare me the details. I just wanted a color. Thank you. Okay. Let's see. So we want to do this guy in orange. Okay. So then for H, we're taking F, the results from F, and subtracting 3 from all of those. So then it looks like we get what? 0, -1, -2, -3, and then -2, -1, and 0. Okay. Let me see. Our X's go from 3 to 3. Our smallest Y is like -3 up to 5. We might have some space here. I think we might have enough space. So let's put some graph paper here. We changed it, but that's fine. Okay. Okay, so we need to we'll put the origin like about here. Matter of fact, let's go like this. So what is that? Okay. What I'm gonna do. Okay, that's decent. Let's copy that. Let's see, we'll put that. All right, so that's going to be our origin. We'll let our positive X go in this direction. Positive Y will go in this direction. Let's go fill. Get a copy. It's a little bit. Undo that last move. Oh, I told you it's been like kind of been throwing tantrums out this morning. Oh no. No, I don't want that either. Let's see. There we go. Okay, finally. All right, so on the x-axis, we need to go 3 on the x-axis. Let me see. So I think we can go like 1, 2, 3. That's fine. 1, 2, 3. Okay. And again, this is the positive x direction here. On the y-axis, I think we need to go up till about 6 and down to -3. Let me see. We go 1, 2, 3, 4, 5, 6. Okay. 1, 2. Okay. So here we have an origin. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 6, 7. And these are our negatives. Negative. Okay. All right. That was an adventure. Okay. Now I think I still have that save, paste. Nice. Okay. So let's graph f of x. So when x is here, it starts at the origin. So I think that point is already there. Then we have what? 1, 1 and -1, 1. So over 1 and up 1. Paste. Left 1 and up 1. Okay. And then we have what? 2, 2, -2, 2, or -2, 2. And then paste 3, 3. And -3, 3. Station. And then if we connect those with a straight edge, we get this image. Let's try that again. Okay, and then I guess we can just copy, paste. Okay. So then what I'd like to do, I would like to get a copy of this. So I'm going to copy pretty much like this. Copy, paste. I will work right about there. Let's get rid of what we don't need. So we don't need this. We don't need that. We don't need these guys. I think we have what we need. Okay. So then G is in green. So I'm going to do this guy in green. Okay. Oh, okay. Let's undo. Oh, it's going to do that thing. Okay. Let me back up. I think if I work here, it'll behave better. This. Let's try this one. Style. Green. What? Why aren't you turning to green? okay. I think I see it. Let's go like this. Style. This needs to be green. There we go. Okay. So now the vertex, right? This one went up by 2. Oh no. Let's get rid of that. Right there. That's decent. I think those are plotted correctly. And then let me just adjust this. That needs to be about there. And that is decent. And then let me go ahead and do the last one in orange. Paste. That's guess it would have helped if I had made a copy of that final one, but that's okay. Okay, that looks decent. And this needs to be an orange. Let's do this orange too. Oh. Get rid of this and this. All right. Oh, there's another one. I'm missing like everything today. All right, and I'll check Zoom in just a moment. Okay, and the vertex is here. Looks decent. Okay, let's go paper. Turn off the lines. Okay. All right, that was an adventure, right? So hopefully you can see the pattern, right? Can anybody describe to me what change in the graph happened as we went from the black to the green, or as we went from the black to the orange? What do you notice? What happened to our graph? If the black is the original, how could you describe that change, that transformation? Okay. Yes.
The black thing shifted upward, and after it shifted upward, it shifted down.
Right. Yeah. So if the black is our f of x, I guess I should. I think the color is anyway. If the black is our original and the green is where we added a positive 2 on the outside of our basic function, it shifted up by 2 units, right? The orange, we subtracted a positive on the outside, it went down that many units, right? So outside manipulations typically follow our intuition. We add a positive, it shifts it up. We subtract the positive, it shifts it down, all right? So we did it by hand. You kind of saw us do that there. And let's see. So here's a type version of what we just experienced. First, it's suggested for us to make a table of values and graph the equations. So you have x, you have your f of x, and then when we say plus 2, okay? So you see the absolute value of x and the plus 2 on the outside shifted it up by 2, and then subtracted a positive on the outside, shifted it down by that many units, down by 3 in this case, okay? So then let's get into like a formal definition for vertical shift. So let C be positive. The graph of y equals f of x plus c is the graph of f of x shifted c units up. And the graph of f of x minus c is the original graph shifted c units down, right? So our first 2 transformations, when we're given a function, if we add a positive on the outside, it shifts it up that many units. If we subtract a positive on the outside, it shifts it down by that many units, right? So then if adding a positive on the outside shifts it up and subtracting a positive on the outside shifts it down, what do you think happens if we add a positive on the inside? Or if we add a positive on the inside, what do you think is going to happen? If we subtract a positive on the inside, what do you think is going to happen? All right.
I think if you add on the inside, it moves to the left.
Positive on the inside. Why did you say left? What makes you say left?
Because I feel like when it goes on the inside, it changes symbol, so it would shift to the left if it was positive.
Okay. So what he's saying is correct, right? It is the reverse. Let's see what happens. Let's see. But it's not intuitive, right? So inside manipulations typically are the reverse of our intuition, right? Because the positive x go to the right. Intuitively, you would think that, oh, adding something on the inside goes in the positive direction would be to the right, where in reality it's the reverse, right? So let's see it in action. So let f of x be x squared. We just talked about this one a moment ago, right? We know the basic shape of that. And then now we're going to subtract a positive on the inside and add a positive on the inside. All right, we're going to see how these inside manipulations affect our graph. A table of values for f, g, and h is given on the next slide. The graphs of the three functions f, g, and h are shown on the following slide. Describe how the graphs of g and h relate to the graph of f, right? So basically, we're going to make a table of values again. So we have our x, our f of x, our g of x, and our h of x, right? So when we subtract the positive on the outside, you know, instead of causing a vertical change, it's going to cause a horizontal change. Notice that positive x is to the right, you know, or negative x is to the left, but we're subtracting a positive on the inside, so this actually goes to the right, which is the reverse of our intuition. You would think that it would move in a negative direction, but it actually moves to the right. When you're working on the inside manipulations are typically the reverse of everything. It's going to be a horizontal change, and it's the reverse of our intuition. Another way to kind of straighten out the direction that it moves, think in terms of zeros. Notice that +2 for that first one makes the inside 0. So this shifts in the positive x direction by 2 units, right? That's going to shift to the right by 2. On the example to the right, a -3 makes the inside 0. So that's going to shift 3 units in the negative x direction. So 3 units to the left. And we see it here. So the blue is our y equals x squared. When we subtracted a positive on the inside, it moved to the right? The reverse of our intuition, and it's horizontal. When we added a positive on the inside, it moved 3 units in the negative x direction. Okay, again, which is the reverse of our intuition. Okay. So intuitively, you know, it's basically the reverse of what you would naturally think. Okay. All right. Let's let that be. So all three functions are squaring functions. G is obtained by replacing x with x minus 2. Okay. So for each point x, y on the graph of f, there will be a corresponding point x plus 2, y on the graph of g. The graph of g is the graph of f shifted 2 units to the right. Okay. That's fine. And it's a similar nomenclature there. So let C be positive. The graph of f of x minus c is going to be the graph of f of x shifted c units to the right, and the graph of f of x plus c is going to be the graph of f of x shifted c units to the left, right? So now we have 4 transformations so far. Okay, outside manipulations typically cause a vertical change, and they typically follow our intuition. Inside manipulations typically cause a horizontal change, or are typically the reverse of our intuition. Right? Okay, let's see it in action. So here we're asked to sketch the graph of this function. Can anybody describe to me the general shape of the basic function square root of x? Like how do you remember that basic shape, or does anybody have a articulate way of describing the shape of square root of x? Going once, going twice. So square root of x, the way I remember that shape, if you think about a parabola, square root of x is the top half of a sideways parabola. So if you take a parabola, turn it on its side going off to the right, cut it in half, you only keep the top half. Square root function is the top half of a sideways parabola. Okay. So for this graph, we're going to implement some of those 4 transformations that we just introduced. We're going to implement them here. So first, let's identify our basic function. I'll just call it f of x. Our basic function. Can't write today. It's going to be what? The square root of x. Again, the top half of a sideways parabola. So then, if we wanted to list out our transformations, usually we do when we're doing multiple transformations in one go, the recommendation is to work your way from the inside to the out. So do the innermost transformation first, which is going to be, we're adding a 2 on the inside. So inside manipulations typically cause a horizontal change, and they're the reverse of our intuition. Since positive x goes to the right, and we're saying plus 2, this actually goes left by 2, right? So we're starting with square root of x function. the first transformation tells us to go left 2 units. Oh, I need to check my attendance. And then that -3, notice that -3 is on the outside of our basic function. So that tells us to go down 3 units. Right? So we're starting with the top half of a sideways parabola. We move it left 2 and down 3, and then that's our graph. Okay. And this is kind of explaining all that. You see it here. So we started with the square root function, the top half of a sideways parabola. Then we went left 2 units and then down 3 units. And then the red is our final graph. Let me check on you guys in Zoom. For any latecomers. Okay, you guys look good. Now I added them. And then let me check here. The bookstore. Unless they moved, it should be in the parking deck. The bookstore should be in the parking deck. We have the version. I mean, the access code is just a code. You might want to. Well, they just arrived to this. They finally finished the deal, so you just have to honestly just keep checking with the bookstore. They should have it. Like, it's just a code, and they should have it. That was something that was resolved, I think, like last week. So I would just reach out to them. I would just reach out to them. And if they're not responding, maybe check in with the mathematics department, the department chair. Just check in with him and see what he says. Because sometimes they have solutions as well. But yeah, it should be the bookstore. Okay, so we've seen our 4 rigid transformations that just changes the position of our graphs. So let's look at this one, reflection in the x-axis. The graph of y equals a negative f of x is a reflection of the graph about the x-axis. Let me see. Yep. If a point x comma y is on the graph of the original, then the point x comma negative y is on the graph of y equals negative f of x, right? So notice this negative is outside of our basic function. We're multiplying the outside of our function by a negative. Versus, this is how it's going to look to multiply the inside of a function, right? But so again, outside manipulations typically cause a vertical change. It's like it affects the y. When we do manipulations inside our basic function, it affects the x. So whenever we affect the y, it's going to be some kind of vertical change. If we affect the x, it's going to be a horizontal change, right? So say our original function is the blue. So we multiply the outside by negative. So it's like our y values go from positive y to negative y. So it flips vertically over the x-axis. Okay. So then the graph of f of negative x, where now the negative is inside our basic function, flips about the y-axis. It's like our x's go from, the y's stay the same as they are in this case, but the x's go from like positive x to negative x. So it flips it horizontally over the y-axis, right? So say the blue is our original graph, and we multiply the inside by a negative, the y values stay the same, but now our x's go from wherever they are to negative x, positive x to negative x. So it flips it horizontally over the y-axis, and that still matches, right? So I think so far we've been saying outside manipulations cause a vertical change, inside manipulations cause a horizontal change. 10 minutes remaining, party's almost over. What a bummer. Anyway, okay. Explain how the graph of y can be obtained from the graph of absolute value of x. Okay. So all right, so it looks like we have like a total of 3 different transformations. So if our basic function, say we start with y equals the absolute value of x, right? We know that image, right? It should be a V shape. We just did it a moment ago, a V where the vertex is at the origin. And again, the recommendation is when we're addressing multiple transformations in one equation, work your way from the inside to the out. So you want to start with the innermost nested manipulation. In this case, we're going to start with the -2. So we're subtracting a 2 on the outside, on the inside, right? So then what kind of change is that going to create? Is that going to be a vertical change or a horizontal change? It's an inside manipulation, so it should cause a horizontal change, right? And the horizontal changes are typically the reverse of our intuition. So because that's a -2, that means we go to the right in the positive x direction by 2, right? So because +2 makes the inside 0, so this is saying we basically go right 2 units. Okay. So then working our way out, the next manipulation that we address is we multiply the outside by a negative. So outside manipulations, it's going to affect our y, so it's going to be a vertical change, and it's like our y's are going from positive to negative. So we're going to flip vertically over the x-axis. So we're going to say flip over the x-axis. Okay. And then we added a 3 outside of our basic function, so that's telling us to go up 3 units. So this is the story or the narrative behind this equation. It basically says start with the absolute value function, shift it right by 2 units, flip it vertically over the x-axis, and then go up by 3 units. Okay. You see the absolute value function, we went right 2 units, then we should flip it upside down. And then I think lastly we said what? Go up by 3 units. And you see it there. The red is the final graph. Okay, so that we saw multiple transformations in one equation there. Okay, let's keep going. So given this f, g, and h, okay. So now we're going to see how does multiplying different aspects of our functions, how does that affect the graph? So we have this f, which is absolute value of x, g, which is we're multiplying the outside by a number larger than 1. And then h, we're multiplying the outside by a number between 0 and 1. Okay, let's fill in the table. So absolute value, then we have our f of x, so absolute value of -2. It's 2, we have 2, 1, 0, 1, 2. Then g, we're taking those results and multiplying them by 2. So this is going to be 4, 2, 0, 2, 4. And h, we're multiplying by a half. So we're taking f and multiplying it by half. So that's going to be a 1, 1/2, 0, 1/2, and 1. Okay. So if we plot these points, right, here's the table filled in. The blue is our original. And then with g, again, we multiply the outside by a number larger than 1, we get the red graph. We multiply the outside by a number between 0 and 1, and we get the green, right? So the way we can articulate this, when we multiply the outside of our basic function by a number larger than 1, we call that a vertical stretch. So it gets kind of like tall and skinny. Like if you imagine, I don't know if you guys know what Laffy Taffy is, but if you had your image on taffy and you stretch it vertically, it gets tall and skinny, right? And then when we multiply the outside, which is kind of makes sense, right? It follows our intuition. It's getting bigger vertically. When we multiply the outside by a number between 0 and 1, it gets smushed vertically. It gets short and wide, right? So we call that a vertical compression, which makes sense. It's like it's a number between 0 and 1. It's a smaller number, so you would expect it to get smushed or get smaller vertically. Okay. So then the graph of y equals 2 times the absolute value of x is going to be the original graph vertically stretched or expanded by multiplying each of its y coordinates by 2. And the graph of 1/2 times the absolute value of x is the graph of the original function vertically compressed or shrunk by multiplying each of its y values or y coordinates by 1/2, right? So multiplying the outside by a number larger than 1 causes a vertical stretch. Multiplying the outside by a number between 0 and 1 causes a vertical compression. We got like 2 solid minutes. Let me see. And that's essentially what this is saying here. It's kind of reiterating that. Or it's like an official definition. And so then here, we've seen to where we multiply the outside by a number. Now we want to see what happens when we multiply the inside by a number. So if outside causes a vertical change, inside manipulation should cause a horizontal change. It should be the reverse of our intuition, right? So if we multiply the inside by a number larger than 1, all right, intuitively you may think, oh, it's going to cause a horizontal stretch. It should get bigger horizontally, where in reality it does the reverse. If we multiply the inside by a number larger than 1, it should cause a horizontal shrink, right? So let me see. Right here in part B, if we multiply the outside by a number larger than 1, it causes a horizontal shrink or horizontal compression. The inside. If we multiply the inside by a number between 0 and 1, it causes a horizontal stretch. It gets bigger away from the y-axis, right? So it still kind of follows the main narrative that we've been saying. Outside manipulations typically cause a vertical change and follow our intuition. Inside manipulations cause a horizontal change and are typically the reverse of our intuition. Okay. So using the graph of this function, whose equation is not given, sketch the graph of the following. I'm just going to kind of go over this a little quick. So notice for part A, we multiply the inside by a number between 0 and 1. So that should cause a horizontal stretch. B is going to cause a horizontal shrink. And then with C, notice we're multiplying the inside by a negative. So it should be B, but flipped horizontally over the y-axis, all right? So stretch the graph horizontally, so a horizontal stretch for part A. Horizontal compression for part B. And then C is going to be this graph, but flipped horizontally. So we flip over the y-axis, okay? Let's see how many more slides I have. I'm just going to do a quick scan before I'm trying to get you guys out of here if my device decides to work today. We're going to have to leave this as an exercise. There's a total of 1, 2, 3, 4 different transformations. So for something like this, you would identify your basic function and then list out your transformation, starting with the innermost nested transformation first. Then we have to leave the rest as an exercise. I think that might be the last one. No, there's this. Yeah, I have to leave this as an exercise. Okay, gentlemen, are there any burning questions? Let's share. I'm going to send this to Box. Let me make sure it's the right folder. Full, traditional, thumbs up for 1, notes, updated daily. Okay, so when this bar finishes loading, you'll receive a copy of anything that you saw me writing. And if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. I'll see you Wednesday, same time, same place. Take care, guys. Peace.
Professor C, I have a quick question for you. I had already ordered my math lab code prior to it was probably since August. And I had gotten an email saying that my order was ready for pickup. But then when I actually got to the bookstore, they said that my code was canceled and back ordered. So I just need to know what I need to do.
And just explain that to them. And let them know that, you just explain that to them and tell them that you're trying to just explain the whole thing and tell them that you're trying to use acquire the discounted rate.
Mm-hmm.
Just explain the whole thing to the bookstore.
Okay. All right. Thank you.
Mm-hmm. Any other burning questions, gentlemen? Going once, going twice. All right, gentlemen. Again, we're going to go ahead and end the session here. From one beautiful mind to another. Enjoy the rest of your day. See you Wednesday, same time, same place. Take care, guys. Peace.